Good morning and welcome to Detecting Deep Fakes with Mice in Laguna GHI. Your speakers this morning are Alex Comerford, Jonathan Saunders, and George Williams. Just a couple of quick announcements before we get started. Stop by the Business Hall located in Mandalay Bay, Oceanside, and Shoreline ballrooms on level 2 during the day, and there's a welcome reception tonight at 5:30. Black Hat Arsenal is in the Business Hall on level 2. The Pawnee Awards are in this room tonight at 18:30. That's 6:30 for those of us not in the military. And finally, please remember to turn your phones off or silence them. And with that, I will turn it over to our speakers.
All right. Great. Thanks, Kevin. And thanks, Black Hat, for having us. So I'm George, by the way, and I'll be reintroducing Alex and Jonathan here in a second. But I wanted to start out by going back in time a little bit. Yes. October 31st, 1938, to be exact. And here were some of the headlines from that day. And as you can see, there was an alleged panic caused by a fake news radio broadcast that occurred the night before on CBS radio. And so this broadcast depicted the invasion of a small town in New Jersey. Of course, we know this today as the legendary and well-orchestrated hoax by a very young Orson Welles, who hired a team of professional actors to perform a live dramatization of the H.G. Wells science fiction work, War of the Worlds. So, reports of the panic were possibly exaggerated, but it's still useful, I think, to draw some parallels between those events and the events of today, the era of disinformation and fake news that we live in today. Of course, today, right, it's very different. Big difference between then and now is that you can craft high quality, realistic content for disinformation campaigns. And the techniques are evolving quite rapidly, from sophisticated face swapping to this puppet master technique you see here, lip syncing, to being able to clone anyone's voice with just a few samples of their speech. The tools are generally available. Some of them are open source. And the techniques have become so sophisticated and available that a lot of officials have started to get very concerned. So a parade of politicians and tech leaders have joined on Capitol Hill to warn us of all the dangers. The idea is that a well-timed fake of a CEO or a politician doing something or saying something they did not do or say may spark some kind of catastrophe, such as destabilizing a brittle financial market or igniting a powder keg-like civil or military conflict somewhere on the globe, a true war of the worlds. Now, whether this happens or not, I think we have an interesting election year coming up. It's hard to say, but we can ask ourselves today, who's being fooled by these fakes? So we did a small informal study, and we asked participants to differentiate between real speech, clips of real people talking, versus fake ones generated by state-of-the-art techniques. And we found that, on average, the median for humans was about 88%. They got 88% right. And compare this to a lot of the state-of-the-art algorithms that were trained and evaluated on the same data set. Around 92% was the median. And as you can see in the box plot there, right, some humans and some machines actually do a lot better. But on average, humans and machines get about 90%, which seems pretty good. But if you think about the millions of items of content that are created on a daily basis, uploaded to YouTube, to Facebook. Even a small error rate means that some of the fakes are going to get through human reviewers and are going to get through automated systems. And possibly worse, some of the genuine content will be spotted as fakes, will be flagged as fakes. So we're going to explore that further in the next part of the talk, the remainder of the talk, and we're going to divide it up into machines and biology. And on the machine side, Alex Comerford of Bloomberg, he'll talk about state-of-the-art methods for generating and detecting fakes. And on the biology side, Jonathan Saunders of the Institute of Neuroscience at the University of Oregon will talk about the neuroscience around all of this. And he'll propose a novel detection technique, neither based on humans or machines. I'm going to hand it off to Alex now.
Hello, everyone. Hope everyone's having a good day today. I'm Alex. I'm a data scientist at Bloomberg, and today I'm going to talk about detecting audio deepfakes with the machine approach. So I want to start with what is a deepfake for people in the audience who've never heard of the term before, a little bit vague on it. My definition, that's a little bit different than what you can find online, is using deep neural network to create human-like data that tricks humans into thinking it's real. So this term is pretty new. It was coined a few years ago, back in 2017, and the public generally associates deepfakes with synthesizing images or video, and specifically synthesizing fake political videos or even fake pornography. But it's useful to think about deepfakes as a function where you input a bunch of data about a person and you output essentially a puppet of said person. So now going into how they're made. So deepfakes are a product of a larger category called generative modeling with the addition of great advances in neural networks and deep learning in general. And what deep learning is really good at is creating mappings from one form of data to another. Examples doing text to speech or speech to text or even faces to faces or pictures to pictures, etc. And with these high fidelity feature mappings, deep neural networks have produced the most fake looking samples compared to any other model. However, it comes at a cost. Training these and making high fidelity fakes requires a significant amount of resources, namely fully representative data sets and a lot of compute. So making good deepfakes is really hard. In one famous paper, Synthesizing Obama, the author mentions that it took over 17 hours of presidential addresses of Obama to come up with these samples that you see on screen. And he also mentions, so one thing is that if you're not a public figure, 17 hours is a lot of data to have just in your pocket about a person. And the author notes that doing training times, that it took about 2 weeks to train these models on a CPU and about 2 hours to do it on a GPU. But what we don't know is the amount of hours it took to do feature engineering, creating these facial masks, fixing lip syncing and teeth, which are all mentioned in the paper, which adds to this difficulty. However, if you want to make a general deepfake, they're pretty easy and fun to do. You can just clone projects off GitHub. You can make celebrity faces, or you can even synthesize voices. So we're going to listen to a clip by DeepMind, a specific architecture that came out called WaveNet.
The Blue Lagoon is a 1980 American romance and adventure film directed by Randall Kleiser.
So a little robotic, but it's pretty good than some text-to-speech systems in the past. And that's kind of where I want to pivot into a little bit of the history of text-to-speech with the goal that we want to type a phrase and output an audio file that sounds as realistic or as similar to a human saying that phrase and reading it aloud. So looking at the phrase, "I've been looking forward to Black Hat all year," we're going to go way back in time to 1999 with Microsoft Mike speaking this.
"I've been looking forward to Black Hat all year."
So a little bit robotic, but it's a concatenative system where it strings together a bunch of phonemes to make words and whole sentences, but not so bad. Fast forward another 7 years, we have a system, Mary 3.
I have been looking forward to Black Hat all year.
So significant improvement, a little monotonic, but we're getting there. And Mary 3 was made by University of Saarland in Germany. And it's using hidden Markov models to generate parameters for a synthesizer. It's a parametric model. And now fast forward again, we have a big product release by Apple coming out with Siri.
I've been looking forward to Black Hat all year.
So to our ears, we can still hear a little bit of the robotiness, but it's getting much better. And we don't exactly know how Siri works, but it's fair to assume that it uses a bunch of different approaches together, concatenative, parametric, and even deep learning nowadays. And so now we're going to fast forward to close to today, 1 or 2 years ago. We're going to listen to DCTTS, which is deep convolutional text-to-speech.
I've been looking forward to Black Hat all year.
So we're starting to get a little bit of highs and lows, pitch, a little bit of interesting pauses, and it's starting to get much, much better now. This work was done by 2 independent researchers in Tokyo. And now the last model that I want to talk about is Tacotron 2, which came out by Google last year.
I've been looking forward to Black Hat all year.
And if you were listening over the phone to somebody like this, I'd be fooled. And if it was trying to talk to me, I'd listen, I'd buy. And so yeah, this is a model made by Google. And this is a deep learning approach, same thing with DCTTS, which is trained purely just by examples, text and audio, and just shown a bunch of them, no handwritten rules. So now that we've heard a few of the samples, I want to go into a first approach, which was taking advantage of GAN discriminators. So we wanted to use GANs, which are generative adversarial networks. Quickly, GANs are composed of 2 components, a discriminator and a generator. One tries to fool the other, and the other tries to discriminate and trying to detect if it's being fooled. And after playing this game, the discriminator and generator become very good at their respective roles. And what we want is a very powerful discriminator, unlike what most researchers want, which is having a very powerful generator generate fake samples. We want a powerful discriminator to tell us what's fake. And so in this framework, we trained an existing architecture called WaveGAN on the ASV spoof dataset for a significant amount of epochs and a bunch of hyperparameter combinations. So we want our discriminator to be nice and strong. However, we found that after training that the discriminator wasn't really powerful enough to generalize to other forms of speech by other models it's never seen before. And we don't think that this training approach is a lost cause. We believe that there's a couple of future directions we can take this approach to really beef up the discriminator, namely giving it samples from different models, giving it richer features, which I'll be talking about in a second, and or doing some sort of multi-phase training approach, like training the discriminator after it's converged inside of a GAN framework in its own separate training loop. So now I'm going to go to our second approach, which we're taking influence from signal processing and using bispectral analysis, specifically using the bispectrum of raw audio as the evaluating feature. And this was shown to work by researchers at Albany and Berkeley. So we're going to take the bicoherence of a signal, which is a calculation to represent higher order correlations in the frequency domain, and quantifies phase coupling across 2 different waveforms. And this is a picture of a small section of the bicoherence of a human saying there are different cultures in different apartments. And it's a nice, pretty picture. We'll talk about how we use that. So we're going to take the aggregated bicoherence by doing a sliding window over this entire waveform and average up all these bispectrums to produce a unique signature about this waveform. And we can see that I have a little 3x3 right here of different text-speech systems saying different phrases, and they look like pretty pictures, but actually they contain information about who is speaking and how they're speaking. And we can take high-level statistical features, namely just the mean or standard deviation, and plot this, and we get some interesting results. So here's a figure. On the left side, every dot is an individual audio recording. On the x-axis is the mean magnitude of the bicoherence of the bispectrum, and on the y-axis is the mean phase. And if we plot for each waveform, color is indicating who is the speaker. We can start to see a little bit of interesting clustering effects going on, indicating which speaker is what. And so we can plug this into an out-of-the-box classifier, namely we used an SVM, and we can plot the decision boundary, and if you fall within the blue blob, you are real, but if you're in the red blob, we call you a deepfake. And this achieves upwards of 95% accuracy on the LJ speech dataset, subset of it. So I want to talk about two takeaways now, that detection with these machines is an inevitable cat and mouse game. And bispectral analysis works for now, but you can easily incorporate these artifacts in these neural network loss functions to try and make sure that these bicoherence artifacts mimic what humans do. And we believe that GANs might be the long-term solution instead to reach this high fidelity discrimination. So here's some references. If you want to download the code to reproduce some of this research, you can find it on my GitHub. And now I'm going to transfer that to Jonathan.
Thanks. All right. Okay, so we want to ask the question, what kind of deepfake detection do we want? So on the one hand, we can just continue throwing data at it. I mean, we're pretty good at that. And that works for now, but it's like, as Alex was saying, it's always this cat and mouse game. But if we want to move towards a more general purpose, algorithm independent, sort of independent of the generation algorithm, deepfake detection, we need to take insights from phonetics and neuroscience, which will tell us respectively what speech should sound like and how the human auditory system processes it. And so with that, I'm going to give you three things today. I'm going to talk about one possible way we can use phonetics to look for new features to detect these deepfakes. Two, one possible new architecture we can implement in our artificial neural networks that's inspired by the auditory system. And then three, a new technique using mice to try and study these mechanistically. So listening to speech is hard. First of all, it's a hierarchical process. So starting at the top level of sentences, we have dear Werner Herzog giving us an example.
Is there such thing as insanity among penguins?
And so that top sentence level is broken down into individual words, but then the atoms of speech are really phonemes. The individual sort of p and n, gwen's the smallest thing you can think of. But each of these phonemes is extremely fast. We have 10 to 30 phonemes per second in normal speech. And not only that, everyone's voice is different, so we have to normalize to the voice timbre, rate, prosody, etc. And so what that means is that the auditory system has to compress its representation of speech. It has to throw away a lot of redundant information that's not informative. And it also has to normalize to each of these features. But it's not just the problem that speech is extremely variable. Because the normal rates of speech, the preceding and succeeding phonemes will influence each individual phoneme. We actually run into this problem of co-articulation. So for example, in these videos, take a look at where the tongue is when we produce the b in each of these sounds. So starting with EB.
EB.
And then
Ba.
So even though the b sounds nearly identical, when you look at the actual spectrum of the sound, the frequencies that are present in it in the center plot here, they're actually not even close to identical. So co-articulation means that we don't have a unique acoustic signature for each individual phoneme. But this is useful because this means that we have this sort of combinatoric explosion of possible speech waveforms that could be used to actually sound like an individual phoneme. And so when generating these deepfakes, if the neural network isn't specifically conditioned to take into account this co-articulation phenomenon, it's possible that it would generate sounds that sound real, but acoustically aren't anywhere near to what actual speech sounds like. And so this is just a possible new vector we can use to target these deepfakes. And so the auditory system is designed to be gullible. Because this speech perception problem is so hard, it has to collapse across these sort of redundant and complex and overlapping feature spaces. And so that's why deepfakes work, is because they might not be acoustically perfect, but because the objective of the auditory system is just to understand speech rather than dissect every possible acoustic detail about it, it's possible to hide in the feature space. And so the little that we know about how the brain actually does this comes from epileptic patients mostly, who need to have electrodes embedded in their brains, and they're patient enough to let us do experiments on them. But we know very little. And so really all we know is that just like some posterior or rear part of the temporal cortex signals onsets of phrases, and then there's recurrent circuitry that sort of computes these sort of trajectories between phonemes. But the rest is basically theory. And so the reason why we can't really study this is because speech is too fast. Basically 20 milliseconds of sound is going to distinguish a b from a p. And neurons are too small for the typical fMRI resolution to resolve. So there are about 630,000 neurons in one voxel. So if our techniques are 1 million times too big and 1,000 times too slow, we can do what we always do as neuroscientists, and that is use mice. So what we've done already is we've taught mice to discriminate between English phonemes. And so in particular, they're discriminating between these consonant-vowel pairs, consonant-vowel classes. So they want to learn b versus g. And so I'll show you a demonstration of the task in just 1 minute. But the general idea is that we want to walk them through a series of stages that increase in difficulty, adding new recordings, vowels, and speakers, and then eventually test them on tokens that they've never heard before. So this is a mouse performing the task. I'm going to poke in the center, hear some sound, got this one right, went and got some water on the right. Here, that one was a g sound. So these are pitch shifted because the mouse audiogram is different, but they're otherwise identical to normal speech sounds. And so they're quite good at it. And so when we evaluate their actual performance, we can see that just walking through the levels of difficulty on this plot on the right, their training set accuracy, it has a wide range naturally, but about 75% accurate. And then as you increase the difficulty going to novel tokens, novel vowels, speakers, and then finally the hardest category, novel speaker and vowel, where there basically is nothing similar to what's going on in the training set, their accuracy only drops by about 10%. And usefully, their accuracy is sort of non-uniform. So each mouse doesn't get everything wrong sort of equally. They have these unique characteristic patterns of what they get wrong. And this is stable across several mice trained on the same training set. So we've also validated this by training them on a different set of, sorry, I should have walked through this plot a bit more. So this plot is broken down vertically by first by consonant pairs, that's the big blocks top and bottom. And then within those, you have different speakers and then different vowels. And then so accuracy goes from black to red from 0 to 100%. So anyway, we compare two different groups of mice trained on different sets of tokens. And they have completely separate patterns of accuracy. So if you take a look at speaker 3 and look at the accuracy for the G's and the B's, they basically totally reverse the bias of the first group. And so this is useful for us because we can look at us as neuroscientists because we look at the ways that mice process speech, but it's useful for detecting deepfakes because we believe that the mice are sort of auditory blank slates, that they can learn really complex feature sets. It's possible for them to sort of learn really complicated classification problems because they have these really complex representations of the classes. So why mice is because we can do this. So this is calcium imaging, looking at the activity of thousands of neurons simultaneously across the entire surface of cortex at 2 different spatial and temporal scales. And so what we can do by using mice is we can actually observe the way that the mice learn these deepfake categories and the way that they compute them. And so what we next wanted to learn is that some of our mice failed to learn the task. We wanted to know why. And so humans have this same problem too, where you can't really hear acoustic contrasts that are outside of your language. And so one common example is that just like some Southeast Asian language speakers can't distinguish between liquids, ers and ols, because in those languages that's not a contrast, that's not a difference that exists in that language. And this is generally true with languages. And so we believe that this is the same sort of mechanism as what causes deepfakes to be effective, because we have these really fast and abbreviated processing rules that become concrete throughout our lifetime that allow us to actually extract phonetic identity. And so to investigate this, first we just start by information is stored in the synapses like artificial neural networks. It's the pattern of weights and connectivity that stores the information. But some neurons have sort of sweaters that prevent new synapses from being formed and stabilize existing synapses. So this is what they actually look like, just sort of staining for these synapses. They completely coat the neuron. But then we wondered, what if we destroy them and let them grow back? Basically reset the set of synaptic weights and connections for these neurons. And so in mice that had previously completely failed to learn the task, they'd been failing basically at chance. So just like on the y-axis, you have the different levels of training and accuracy. These mice that were at complete chance for several months, we injected this enzyme that digested their perineuronal nets, i.e. resetting their sort of synaptic weight matrix. And then suddenly they were able to learn. So suddenly they were able to learn to hear acoustic contracts that they were not before. And so why this is useful for detecting deepfakes is because it gives us a mechanistic clue into what we can improve in our networks. So not all neurons wear perineuronal nets. Indeed, it's just these types of local inhibitory neurons that pool excitation and then have this sort of global non-specific inhibition of the cells around them. And so we think that this is computationally distinct from regular excitation that we use in artificial neural networks, because these local inhibitory neurons integrate the recent past to steer this recurrent computation. And this is the way that it stores these sort of long-term stable auditory percepts. And so finally, we think that it's time to do what we did with the visual system to make convolutional neural nets, and take inspiration from the auditory system in order to use that to make the next generation of deepfake detecting algorithms. And so to do that, we think the technique that we should do is training mice to detect fake and real speech. Thank you. Oh, I'll give you some takeaways just as a summary here. People are still pretty good at spotting fakes, but it's always going to be a cat and mouse game. And so the real way to solve this problem is to take inspiration from phonetics and from biological neural networks. Thank you.